Hey everyone, how are we doing? It is back to office hours here, and we'll get some work going. If anyone's in the chat, what do you want to cover? What do you want to do? It is exam review advice 2. Ella, good to see you there. What do you want to do, Ella? I've got water and everything here. Water. All that good stuff. My wife packed a lunch for me, so I'm so lucky. What should we do? We had a lot of in-person office hours today. A lot of good work done. Yeah, what do you want to cover, Ella? You name it, we could go in depth on something. Go over a topic of your choosing. You pick whatever topic you want to go in depth on. Got the screen up here. Let's see what people say. It was like, hair's going crazy. What topic should we do? What topic? Hardest chapter is usually chapter 5 for people. Okay, let's do P-value stuff. A lot of people don't understand how the whole P-value thing works. So let's do chapter 5/chapter 6 P-value understanding. A lot of people just, it's tough. People don't understand how the P-value stuff works. So chapter 5, they are used to check normality. In chapter 6, they are used to check correlation. Okay, so the general broad idea of a p-value is the following. I'll make this bigger here so it's easier to see. There we go. P-values allow us to see if something is statistically significant. We generally say they are statistically significant if the p-value, which stands for probability value, below, I want it to look like that. I think that looks cool. Is below 0.05. That's a key number to know right there. And what this means this is where usually people get confused on what the deal is with a p-value, because they allow us to assess statistical significance by telling us if what we saw was likely or unlikely by random chance. And when we have something unlikely by random chance, the p-value will be low. When something is likely by random chance, the p-value is high. So we need to probably put a null hypothesis here. When checking normality, the null is data is normal. Now I know it's counterintuitive to think that things are normal to begin with. But the starting assumption or null hypothesis for this chapter is the data is normal. So we're going to highlight this right here, and the starting assumption there is data is normal. And then for here, counterintuitive also, is no correlation. Now, what we want to do is think about what is likely to see if the data is normal. So we're going to put here a likely result. And this would be a high p-value, very probable result. And then we can put here an unlikely result, i.e. low p-value. So think, if the data is normal, what would be a likely thing to see? If the data is normal, we're only focusing on this first one here. If the data is normal, then what would be likely to see? Well, what's likely to see is the data. It'll look, the shape of it. Good question right there, Ella. The shape of it. It'll probably look like this. How do we check normality? So how do we check normality? This is called a goodness of fit test. So when we check normality by fitting a normal curve over it, we see if the normal curve is a good fit. Maybe we'll draw a nicer color than that. That looks mad. And we'd say this is a good fit. We're like very happy that is a good fit on the data. The normal curve fits that data well. And so we think the data is normal. And what we saw or observed in the data was something that conformed to what is likely normal. Now, if you go over here to the unlikely result, remember, we're assuming the data is normal. So if the data is normal, what would be unlikely to see? Then what would be unlikely to see if the data is normal would be something more like this. And we're going to get a monster man here. So if we saw data that had this sort of shape, which is a monster man, he's going off the screen right there, crazy looking monster man. We got a right skew monster man, right to the high, left to the low. This monster man is pulled to the right side. Then the normal curve would not be a good fit on this data. If you try to fit a normal, it's not going to fit very well. You notice it's got areas that the normal's not fitting in, and that doesn't look good right there. So this is not really a normal distribution. We can't draw a normal curve over it. And even I had to skew that normal because if you draw a normal, it's not going to end up working really well. You've got areas where there's too little or too much data, no matter how you draw a normal, so it's not working. Does that make sense? Tell me, Ella, if this is making sense. This is Chapter 5, Checking Normality. And what you have here in Chapter 5, you're using the goodness of fit test. Yeah, Harrison, let me know what you're wondering about. This is how we check it. Oh, I could try to draw that next, Harris. You got it. Harrison, excuse me. This is how we check normality with the goodness of fit test. So this one would have a p-value of something like, if we do a p-value of like 0.80, and that's not a correlation, that's a p-value telling us that this is a likely thing to occur if the data is normal. And then over here, this one would have a p-value of something like 0.00001, meaning that this is an unlikely result if the data is normal. And tell me if this is making sense, Ella and Harris, and then we'll do the next one, then I'll do Harrison's question right here. But this result over here on the left is a good fit and a likely thing to see if the data is normal. If we assume the data is normal, this is a good fit of the curve. P-values can only be between 0 and 1, correct? And they really never hit 0 because what you observe is possible but very unlikely. They approach 0. If something occurs, it has to have a probability that is non-zero because it did occur. But p-values range between 0 and 1. And if this curve was perfectly normal, then the p-value would be 1. Like if this was a perfect normal, because that would be the most likely thing to see as a perfect normal. You don't have to get a p-value of 1, but this curve would have to be perfectly normal because if we assume the data is normal, what is the most likely thing to see then? A perfectly normal curve. So how would the next one look for this next idea of correlation? So we need to mark right here what is likely or unlikely. So we're going to do the same idea, but we're going to do it with correlation on what is likely or unlikely. And think about it. If there's no correlation, the points should probably look what? If there's no correlation, think of a word, the points should probably look very what? If there is no correlation, then the points should probably look pretty random, right, on a scatter plot. And then what would the value of correlation be close to? So if there's no correlation, this is a likely thing to see. Remember, we're saying if there is no correlation, what is likely? This is likely given no correlation. Like if there is no correlation. And then the value of correlation would be equal to about what? Which is not the p-value. That's not a p-value. So what would the value of correlation be about equal to? It'd be close to this, which is a correlation likely by random chance. When you see the correlation values closer to this. Here's a hint. 0, Harrison, great job. It's 0. And so that is a correlation likely by random chance right there, big 0. And then over here, an unlikely by random chance correlation might look something like this. What is this value of correlation close to? You should be able to estimate this value of correlation. This would have a p-value that is very, very small. It would have a p-value like this because this is unlikely to occur if there's no correlation. So if there is no correlation, this would be an unlikely result given no correlation. Great job. It's closer than great job, Bella and Ella and Harrison. This is going to be an R equal to maybe something like negative 0.96. Make sure the negative is key because the direction is going down. So must have negative. It's not quite perfect, but it is closer to -1. And this one would have a p-value over here of something like 0.99 because this is extremely likely by random chance. Who thinks they follow along that you have to know your starting assumption? This is our review sheet right here. But this has been a quick review on what is likely or unlikely to occur given our starting assumptions. So you have to know that on Chapter 5, when we're checking normality, the starting assumption is the data is normal. And on Chapter 6, the starting assumption is no correlation. And then we can look at what was likely or unlikely given those results. And then Harrison has a good question here too. But let me know if you have follow-ups. This is kind of a review sheet on it and telling you what you would expect to see or not expect to see. And this is the goodness of fit test right there. Harrison asked, the middle 50% of a data set will be within 2 standard deviations of the mean, formally distributed. That'd be false. That'd be false. to Harrison's question. And what should we do next? Good question, Harrison. And feel free to drop more questions because this is normally distributed for normally. Oh, that says for normally. Yeah, I was like formally distributed. The answer is false. So with this right here, the middle 50% of data. Well, if we go out 2 standard deviations, as this says, it says go out 2 standard deviations. What percent of the data will be within 2 standard deviations? What percent of the data will be within 2 standard deviations? What percent of the data will be within 2 standard deviations? So we draw it out right here where we have 2 standard deviations, and 95% will be within 2 standard deviations. 95%. The middle 50% would have to be tighter inside of here. It can't even be outside of 1 because within positive 1 and negative 1 is the middle 68. How do people feel about this? Douglas, good to see you there. How do people feel that the middle 50% would have to be within 1 and negative 1? And we can confirm this if we go over to the applet. If you go here to the applet and you go to find x using this, you go to here, the middle 50 is between the z-scores of positive and negative this. So you can test your knowledge of the 68, which is within plus or minus 1, 68.26, or 268 or 9. Oh my gosh, look at that. And then 95.449, 6, 9, that's, I don't know. There we go. And then 99.73002. There we go. But we usually say 68, 95, 99.7 because there's always more decimals. So usually we say 68, 95, and yeah, there's 68, 95, and 95, yeah, 449. But how are people doing on this? Does this make sense? That the middle 50% would have to be even tighter. I just broke the app. The middle 50% would have to be even tighter than the middle, that's the T-curve. And we go here to the middle 50%. What other questions are there? We got a little bit of time. What should we cover? We could do another review thing. We talked about p-values, which is a really good, tougher topic for people a lot of times. What other topics are there? There's so many tests this week. Oh, tomorrow's test too, right? Anything that will help us? Let me think right here. I'm trying to think of like every chapter for the test. Anything that will help us? No, don't be scared. Test 1 is one of the easier ones. I'm stressed. No, don't be stressed. There's at least some people have taken the test, done all right. Some people take the test early. Don't worry, test. Here's the thing too. If you've been doing all the work, I like that, Douglas. 1,000 points for positivity. If you've been doing all the work in the class, it's hard not to make a B. Just remember that. Worst come to worst, if you're doing all the work, it's not that I'm promising you a B. It's just hard to not make a B. Like, you have to do extremely poorly on the test or not be doing the work. Yeah, the practice exam. We got under review 1. I didn't type her 1. Review 1 right here might even be backwards on this page. Nope. You really. So review 1 is where all the practice materials at. I would say doing your Canvas content again. Coming to class is huge, which I know people in here have been doing. Because I do basically give some hints to the test. I don't tell you test questions, but I do a little teaching the test moments. And then we give small hints. If I was in the class, I'd be going through these videos right here, especially if you look at something like this. Man, there's Brian long ago. Back in the day, Brian. This is like 6 years ago. Just do the same thing. Here's a little bit shorter. So when this right here is reviewing for you, I don't use this screen as much anymore. Maybe I should. Maybe it's a good way to do it. But we're reviewing if data is skewed, use the mean. If data is skewed, use the median, and use the IQR. If data is more normal, use the mean standard deviation. Pretty much. They pretty much cover. That's why I have this warning before them. Speedruns are like cliff notes. If you want everything that could be on the test, but not in a like I've said everything, you can go here to the where is it? I'm gonna say a lot. There you go. This has pretty much everything right here, and we can just ask you these things different ways. So you see, like, recognize a trend in a time plot. Yeah, we haven't really done that one much. But a trend in a time plot would just be, you think about how to do that. Oh no. To recognize a trend in a time plot, you would just have like year from like 1900 to 2025 present year. You could do like home price, like the average price of a home in America, and you could just do like this. And then, it's crazy. Actually, it's more like, yeah. Made a study sheet with topic. That's what I'm currently looking over. Nice job. Yeah, and then the videos I have, the speedrun videos are really good because they go through pretty much these. We've updated them a little bit, so it's hard to like redo a video every semester. But if you go to like chapter 5, like there's the checking normality, which we just covered. If you go to the chapter 5 speedrun, you'll see I'm using the sheet right here. And I've got everything marked. I actually went through and added all of those things in here so I could kind of remember like the 68, 95, 99.7 rule. Z-scores is a ruler. So you can see all the different concepts and what I'm covering at what point. So, I mean, the normal curve takes a while. That's a lot right there. Man, that was a lot of time on the normal curve, the 68, 95, 99.7. And you can just see the individual things, the goodness of fit test, what are outliers, things that are more than 2 or 3 standard deviations away, more extreme. David M. Lane examples right there showing how to do solves. That's an applet we have used. But showing how to solve applet questions and things like that. So knowing how to solve questions. And that's kind of what we want you to be able to do. So, yeah, it really comes down to just reviewing and knowing how to do these. What should we do? We got enough time to do at least one more topic here. What should we do? I could try to write you true falses. I could go through and write a bunch of true false questions right now if you want. You can see how many you get. I'll just come up with questions. Then you throw them in ChatGPT and ask it to come up with 20 more. Yes. Okay, let's do it. Let's see how many true falses you can do. Okay, you ready? Let's start. I'm going to go through like 2 per chapter. Okay, you ready? So these are all true or falses, true, false. So just make sure to say true or false, and then let me know like question 1 or whatever. Okay, here we go. Feel free to put like 1 true, 2 false, 2, 3, 4, whatever. Trying to think chapter 2 now. I'm doing like 2 per chapter. I want the mean. No. He doesn't even know. No, this is mosaic plastic contingency tables. So I can put them beside the table over here. Chapter 4. Keep trying to answer and then we'll review. I'm on chapter 4 right now. What? What'd I do? I broke it. Thank you. Oh, no more answers yet. Oh, no, because I didn't put the 8 there. That's why I got mad at me. There we go. Okay. Keep answering. I've got a pivot now in chapter 5, chapter 6. I have no idea what happened. Be kind of nice. That'd have been nice for all of them. I could put true false. Chapter 5. chapter 6. I have no idea what happened there. 2 more, chapter 6. Okay. And people are saying for question 1, it is true. That is very true. That's a fact. We'll put a red and green. We'll do pans rather. 1 is a fact that the identifiers are categorical, special case categoricals that they will not ever repeat. If you see something repeating, it is not an identifier. That's not how identifiers do. Random events must be equally likely. That is false. Think of the lottery. Always try to think of examples. A lot of people, I've seen people put true for that. That is almost like a test question. And I see people put true for that. And it's like, well, the lottery. You might be thinking coin flips. Yeah, some random events, like things that occur randomly, can be 50-50, but nope. The mean should be analyzed and interpreted for all data. That's false, especially for highly skewed data. If data is very skewed, you should use the median because the median is not impacted by outliers. So the median is used for skewed data because it's not impacted by outliers. And so that is false. And the median is not impacted by skewness or outliers. So very important right there. The marginal distribution displays one variable at a time. That is true. That is on the side of a what graphic or what graphic? What graphics have marginal distributions? Can anyone say it in the chat? A graphic that has marginal distributions is one of the graphics names is what on the margins of it? Do you remember? I'm on top chat. What am I doing? What graphic right there? It's also the graphics down here. So the bivariate categorical have marginal distributions. Contingency table or mosaic plot. I'm going to throw some people's points. We haven't thrown out points lately. Contingency table or mosaic plot have mosaic. Yep. Have marginal. And then did people say for number 6? People are saying true. 6 is true. That the conditional distribution is used to analyze to see if there is a relationship. We look at the conditional. And I should show an example of this just so people can see it visually. I mean, I can see it in my head, so it's like I should show you. If you're looking at legendary Pokemon by generation, we're going to treat generation like it's a categorical variable. So I'm going to make it ordinal, which is categorical. And then we're going to look at legendary Pokemon by generation. And that's 2 categorical variables. And you can see there's small differences where the later generations of Pokemon have more legendaries. And so these are the conditionals, given it's a Gen 3. This is the marginal over here. You can also see Gen 1 has more Pokemon, which is a marginal. The marginal is down here across the bottom. The marginal is across the side. The conditional is within. Does that make sense to everybody? This is a mosaic plot. This is a contingency table, which shows the same information, but shows the counts of the data. And right there. So there's the marginal on legendary, the marginal on generation, and conditional giving something as Gen 1. There's only 6 legendary. Gen 1 has 160 Pokemon in it? Oh, because they're counting like Mega Evolution or whatever. I was like, what? 151. Everyone knows that. Yeah. Go down here and go to Gen 1. Gen 1 ends at Mewtwo. That's right. On Mew. Ooh. On 151. The original 151 Pokemon. You get some Chikorita and Bayleaf and yeah. Oh my gosh, what am I doing? Clicking away. My gosh. Okay, here we go. So that is very true. Side-by-side box plots analyze 2 categorical variables. True or false? True or false? Number 7 and 8. Side-by-side box plots analyze 2 categorical variables. The answer is on the screen right here. True or false? Side-by-side it is false. Don't worry. We're throwing you some points right here. It is false. Side-by-side box plots analyze because box plots are quantitative. No, don't worry. It's points. We practice. Good job, Bella. Practice. And then side-by-side box plots are categorical quantitative. Categorical is mosaic plot contingency table. So this is the bivariate categorical. There's side-by-side box plots under cat quant. You have to trace up to the quant and over to the cat. So it's a categorical X and a quantitative Y. And so you can do the analysis over here on something like you can compare legendary Pokemon on their attack. And then you can see here side-by-side box plots by putting in the quantiles on it. So there's side-by-side box plots. And other ways you can do the graph builder way of doing it. Also good. And then you go here and throw in the legendary on the bottom and throw in a box plot, and then you throw in the 5-number summary. So knowing how to analyze and look at data is very important. And there's the side-by-side box plots. We want to make sure you can make data from this class and analyze and explain concepts with data. That's what we do. And so outliers are 3 IQRs above Q3 or below Q1. IQR stands for the interquartile range. Are they 3 IQRs above Q3 below Q1? Is that how they work? Are outliers 3 IQRs above Q3 below Q1? True or false? Don't worry about being right or wrong. It's just practice here. Are they 3? Well, this is an IQR. That is false. They are 1.5 IQRs. And so you can see this is the length of an IQR, which is the exactly 1.5. Yep. So this is going to be about 30 higher on the true. It's hard to see. And this is about 25 higher than this because that's the length. There it is. It's not where the whisker is at necessarily because sometimes you get weird data. Like you get data like this, a lot of zeros. You get like 2s and 3s and 4s and 5s and 6s and missingness. Apparently, we have missingness. And so when I box plot this, the bottom of it's going to be all bunched up. So you see the bottom's all bunched up, and there isn't even a bottom whisker. It's because the min and the Q1 are in the same spot, and the median is there. So the IQR is 7.5, and then if you even go one IQR, you're not even beyond the data. So if we go here and start making changes to this, we do redo auto recalc. We could try to make an outlier. It's going to be about at it's going to be about 11 or 12 higher than this. It's going to be, if we go to 20, we should be there. Yeah, there we go. Is it? You don't see where the fence is at. This should be inside, yeah. So somewhere around here is where the upper limit is. It's a very weird one. It's not the easiest to calculate where the upper fence is at. Yeah, it's going to be at, is it that on the dot? I bet it is, because now if we go 18.76, there it is. So that's where the upper fence is at. We could calculate it mathematically. You do not see the upper fence. It is just 1.5. If you think about the length of this IQR, it's you go here and literally mathematically go 1.5 IQRs, and that's where the upper fence is at. Does that make sense, Harrison? You do not see the upper fence. You do not see where it's at. There's a fence right here that denotes the whisker can go this high. So if I put something here at like 17, the whisker will extend to it, but the whisker only goes where you have through data. And there's a magical fence you can't see, and there's also a fence down here we don't see. So if we went down here to the lower side and 0, and it's like 11.5 higher, right? It is 11.75 higher. Oh, yeah, I have to do a bunch of math. So 11.75, it's going to, oh, because down here, that's easy. So we just go here and go negative 11.26. And there it is. Now if we go to negative 11.25, that's within the fence. Is that making sense? If you go to negative 13, that's outside the fence. There's a magical fence you don't see right here, 1.5 IQRs below, that the whisker can extend to it. You don't see it. Don't see the fence. A lot of people think, where's the fence at? You don't see it. It's just a graphical technique. Kind of went into a lot of detail on that, so let's get through the last few because I got to go to class in 13 minutes. So that is false. It is 1.5. 1.5 is the answer right there. PValue charts can analyze all different types of data. Very, very true. And we do not analyze identifiers, though, because they're here to identify. You rarely ever analyze them. Normal models should be used with all data. Very false. Normal data should be only used for unimodal symmetric. Data needs to be unimodal symmetric. When checking normality, a goodness of fit test with a high p-value means our observed data is likely from the normal. That's what it means. What we saw was likely by random chance, given that it is normal. That is very true. Correlation of 0 means no relationship between the variables. No. Because you can have nonlinear. Correlation of 0 means what? No what relationship. Correlation of 0 means no what relationship. Correlation of 0 means no what relationship. Because this has correlation of 0. It has a relationship, but it has no what relationship. So correlation of 0 doesn't mean no relationship. Correlation only measures what relationship. Linear, great job, Elizabeth, right there. It only means linear. So that's false. Correlation of 0 means no linear relationship. It's the true fact. A high p-value for correlation means that correlation is closer to what or what. Last one here, is it true or false? The last one to finish off. A high p-value for correlation means the correlation is closer to 1 or negative 1. A high p-value for correlation means the correlation is closer to 1 or negative 1. And we did something earlier. Let's help out with this. High p-values are not necessarily good or bad. They just mean whatever they mean for the context of the data. I'll go back to that review screen here. What do you think for the last one, Harrison? And then I'll bring it back up. High p-values are not necessarily good or bad. They just mean if we reject the null or fail to reject the null based on what we saw being likely or unlikely by random chance. Ooh, well, wait, yeah, so is this true or false down here, Harrison? I think you might be on the right track. A high p-value for correlation means the correlation is closer to 1 or negative 1. True or false? Last one right here. A high p-value means the correlation is closer to 1 or negative 1. It's false. A high p-value for the correlation means the correlation is closer to 0. You might have been implying that right there. So here's our review sheet. And you have to realize that we're doing the idea of p-values for two different topics because when you check correlation, you assume no correlation. And the thing is, do you want to find no correlation? Then high p-value, good. Do you want to find correlation? Then low p-value, good. It depends on what you want to find, Harrison, because like p-values are just probabilities, and they tell you if what you saw was unlikely by random chance. It's not necessarily that they're good or bad. Maybe you don't want to find a correlation. So you're like, yeah, high p-value, woo, no correlation. Of course, it could also be, you could also have a nonlinear. You could be like, no correlation, but there's a nonlinear aspect to it. So it just depends on what you want to see. That would also have a p-value 0 because it's no linear. Correlation only measured linear relationships. So that would still have a high p-value because there's no linear correlation. And then the normality one is when you're checking normality, you're trying to see if what you see is likely given the normal curve is the proper fit for the data. So this would, if this is a perfect normal, it would have a p-value of 1, where this one is unlikely to see if the data is normal. So does that make sense? I'm going to head off because I have class in 10 minutes, but that was true falses. I don't know when we started. Sorry for the shorter office hours. Let's go here and say test 3, test 2, test 1, true or false. Test 1. True/false. You're welcome, Ella. We'll be doing more streams tomorrow. We'll be doing class. Till then, bye for now, everyone. Bye, Douglas. Bye.